Okay, before the break, we were kind of looking at some stuff about vectors and just a couple basic ideas from them to get us started on what they are, mostly for debugging. Just a couple little points that we will need when debugging games. For the most part, what we need to do with vectors is built in. Let me start searching for this. Vector in Godot. Should pull up the doc on the top of the docs. And I'll take a nice little description on there. So we have vector objects, straightforward. Once we have a couple of them, we can they're objects, so we can access any of the components inside of them. B is a two-dimensional vector, so we can access the X and Y components separately or deal with B all at once. So like here's vector addition. A is a vector and B is a vector. So that results in adding a vector. So you can see coding it's straightforward. You're mostly going to need it for debugging. So when debugging it, think about the arrows. Scalar multiplication, which division is really multiplied by the fraction 1/3. So divide by 3 is the same as multiplied by the reciprocal. So multiply by 1/3, which is probably what it'll look like on your quiz. So on the quiz, you'll see one, it won't have division there. It'll be like the vector B times 1/3 to replicate what's written on highlighted on that line right now. But that's something you learn in elementary school, right? Division is multiplied by the reciprocal, so it gives us less operations to write. We do everything with addition and multiplication. And oh yeah, and then there's position. A position vector plus a velocity vector is going to give us the next bit of time. You can read through there as it gets more complicated. When we get in kinematics, we'll use vectors a lot. There's dot product. We don't necessarily use that. And game's a whole lot, but it's coded in there. And then the cross product is coded into the shaders we'll use. But you can see it's just it's built in there. So A and B are vectors, so we just do A vector dot cross, and then that function already knows how to handle all the multiplication and addition for the cross product. Same thing if we ever need the dot product. But we'll mostly be doing adding and scalar multiplication, which we can see here somewhere, scroll past it. Yeah, just use our regular operations. So just add two vectors, just make sure you have the negative signs in your vectors, and then multiply by a number. Fairly straightforward. I'm going to do this really quick. Yeah. The other thing to go over this week is graphics, so it'd probably be best just to do that all on Wednesday. And then we'll look at vector stuff. So then we can open up an example here and look at this in some code. And arbitrary stuff. I didn't necessarily think ahead or plan too far ahead. I might do this, but it's not necessarily a thorough example. I'm not even going to give it a name. I'm just going to click the create folder checkbox. Yes.
Are you going to have us like build a game? I mean, like export it into like an executable?
Yeah, we'll be doing some building. When we get to VR in week 7, we have to build it.
Would that be similar to the video that you had made extra in the Python class showing how to?
Oh, it's not that.
Export the.
It's in.
Oh, that was something different. So that was just the next step that we wouldn't be taking to that. Yeah, it's just yeah, it's just this button right over here. It's just this export button. But we have to right now, I don't know how to export to anything. So, the free ones. So Xbox, PlayStation, Switch. Oh, yeah. I don't think we can build we can't build for Nintendo. So build for Nintendo is just offline. But Xbox, PlayStation, what's the Steam and
Steam Deck.
Deck? Yeah. Those cost money to build for. So it's the same thing. All we do is we pay the money and then we download their code and then we have the Steam Deck option here to choose from. So it's not complicated, but
I think it's like around 1,500.
Yeah, but the main consoles it costs money. There is some movement underway to do that and kind of work around with open source things, but they're licensed proprietary stuff. Nintendo just won't let us build for Nintendo. You have to work. You can only build Nintendo games if you work for Nintendo. They're very, very precise, but they're right. Nintendo predates video games. They
Toy manufacturer, right?
yeah, toy manufacturer, but they are also an old samurai game. A lot of those, right? Toyota and Honda are like that for cars. Hyundai is not. But they're old samurai families. It would be dishonorable to make a bad product. Harrio does that. Harrio would be the one that does that. They currently make.
Come on, Nintendo was some of the shit they've been pulling. Come on.
But yeah, it's for some of them, yeah, not as strict as they once were or something. But Nintendo, yeah, they're an old family from the samurai culture. And
Nintendo is infamous for
they're not going to dishonor the Nintendo name, so they don't let anybody in there without being part of. Yeah, they can't build for Nintendo games, but getting a job for Nintendo is not as hard as like for Apple, because the same thing happens for Apple. You're not supposed to code for Apple devices unless you're for Apple, but it's really, really hard to get a job with Apple. Nintendo, if you have a good game, they will hire you as a project manager and then just have their programmers write your game. If it fits their standards. That's another thing, right? If anybody could build, inappropriate games would start showing up on Nintendo. I'll just say it that way.
That's true. Look at Steam.
Yes. So just like Steam Deck, if anybody could build a game for it, very, very inappropriate things would start showing up on there, and Nintendo just will not have that. But if you have a good game idea, you take that to Nintendo, and they will make it, as long as it's a good game that would be appropriate for children and people of all ages and all of the Nintendo standards. But then other things, building for Android, which includes the Steam headset, Facebook, Meta's headsets, all of the headsets except Apple. Building for those are just Android devices. So, and building for Android's free. So we just load that in, right? We just add an Android build.
There are PC games that are just like, you can get PC games from not just Steam, from all the places too. So is that just like is that a different way of exporting?
Yeah, basically. So like export, if I click the add button, these are the free ones. So for Windows, for web, so you can build it for Mac OS, but not. Notice you can build it for Mac OS, but not iOS. So Apple is like restrictive in some places, but not in others. What's that? Oh, it is on there. That's been added since the last time I looked at the list. I guess they're letting people build for it. Used to you build the Mac version and then you could get permission from Apple to release it as an iOS one. Because they're more careful about the phones than the computers. But yeah, all of those are free, and then we can get other ones.
Do like Windows desktop, like what?
Yeah.
It's almost like
what happens when we hit run?
Yeah.
Yeah,
Sitting
get-
on Android on Godot is the pain.
Well, you'd have like a desktop icon.
You have to log into some sort of service, then get some files, all sorts of crazy stuff. And once
Yeah.
it's done,
We will see that though, to answer your question. So for now, let's just do something in 2D, some 2D vector stuff. The icon, the Godot, or it actually works better if we say Godot. That way the Godot robot, that's the little logo, always comes with things. We'll see how I have to change that. So I gotta get Zoom thumbnails out of the way. I always forget to do that until they're like actually in the way. Well, we have a whole bunch of values here already. As soon as we drag that in, it turned into something. And a whole bunch of values that we can't really separate. So this is a vector, right? A vector made up of other vectors. In particular, our most important one here is the transform. That's one we'll see over and over and over again. Where is it located at? How is it turned? So we turn it. Notice where it's turning at. Yeah. And how's it scaled? I don't have a dragger for the scale, so I just make that 4 times bigger in the X direction. They like them together, so undo that. The little that's supposed to look like a chain link. There beside it, that locked them together, so make it 4 times bigger in the X, keep the Y the same. Location, rotation, and scale. Those are going to be very, very important. Let me go ahead and reset these. I want to do something else before I do that. I want to be able to use those, and I could add a script and just start from scratch, but there's some pre-built scripts we can use. So here on the basic node for the world, I'm going to rename it that. I'll call it root. The root node for our scene, we always want to have one of those. It's probably just a basic 2D or 3D node. We're going to give this a save and call this world. I'm going to hit the plus sign and add a child to it, and I'm going to add a character body 2D. Notice the inheritance. So there's basic node, then there's collision object, and a physics body, which means we have a boundary around it and other stuff we can do. And then character body, the blue icons are for 2D and the red icons for 3D or pink or whatever color that is. And now I'm going to drag that image up there and make that image a child of that character. Maybe.
Make it local or whatever. You need to right click on it, I think, and then
Oh, fix all these first.
you need to like expand it out because everything's there.
Oh, actually, there's nothing there yet.
Oh,
So I have to fix the errors. There's no shape, so it can't collide or interact with other objects.
right. You got to build up the other
We
half.
have to build certain aspects to it. I don't know why the image wouldn't in there. I was expecting it to, but
you could put a sprite 2D in there and then drag the SVG file into the.
yes. So all the components for it. So sprite is an image that refers to something we don't really use anymore. It was more efficient whenever we had a spinning hard disk, and we put lots of images in one file. So then when that actual disk would spin and the read head would move, we only had to move it once, read that big file. And then a sprite is a section, each image that we put in that larger file. That's actually slower on SSD drives. Servers still have those spinning ones, so it makes a difference, but we use the word sprite for an image. An image, right? This one's not animated, so I'll just add a sprite to it as a child of that. we're gonna be doing a lot of this. And then this error message, there's still no collision. So I need to add some sort of shape, make that error message go away. On 3D, it automatically fixes it.
I think it does. You just have to put a collision shape 3D.
I'm gonna go with mesh instance, that'll fix it.
No, you have to use a collision shape 2D.
Oh, this'll work. In a couple of steps. The mesh instance.
Doesn't character body need to be a child?
Then I think I can drag this up here. So now that mesh has some sort of texture. Well, it should. Oh. Then a plain mesh. So let's scale this out. Why is it not scaling out? Did I go the wrong way?
Oh, it's a plane. So you gotta-
Oh, I'm looking at the wrong side, ain't I? Yeah, I'll go back to the image. That's probably a little bit easier. I was trying to do it different ways. And what we're gonna do most often is just make it a sprite. So I'll just drag this over. Then I'll make this a child of that. There we go. I'm sure. We haven't dug into making a game very deeply yet, so I'm just looking for. There's lots of ways to do this. So I have a character body and some sort of image to it. We will see better ways to do this. But notice this vector for position, and we set it for 0, 0. Now we have that origin of where that thing's located. And the image is a child of the character. This is also 0, 0. So I move this 32, 40. I'm on that. 24, 140. There we go. That way it's all the way on the screen. We use that vector, the XY vector, which seem like separate components, but we were looking at earlier. Think about that position as the arrow from the origin to that position, which actually drew that arrow in it. Because we just saw that it goes to the center. So to the center of that thing, from the origin to the center, probably in a straight arrow. Hopefully y'all get the idea there. We want to think about it that way. So that if we want to move it, fall straight down, we could just change our Y component in that case. We want it to go over to the right. Should just need to change our X component. So those are actually something that we expect to have every time. At least from a character body, right? I chose the node character body, which indicates that it's something that the player is going to control. If we add a script to it, we'll talk colliders and stuff when we get to physics. I think this will still work for this. So I come up here and add a script or attach a script to the character. Notice that it chose a specific template already. The third box down, yeah, third box down, it already tried to give us a specific, it's not starting with an empty script. Create that. And a couple things already built in there, speed and velocity. That's fairly straightforward. Velocity is speed with a direction. So it's the vector version of speed. So for example, if you drive 30 miles north up an interstate at 70 miles an hour, and then turn around and come back down country roads, again, go 30 minutes, but at 25 miles an hour, you're not going to get to the same spot you started at, right? Because we have it's speed, the vector version, speed with direction. So 70 miles an hour north for an hour is going to take you 70 miles. Choose some numbers with easy math. Then we turn around and go half that speed. 35 miles per hour south for 1 hour is only going to get you halfway back to the starting point. Then overall, there's a displacement vector. So overall, the total displacement is 35 miles. Did I say north or south first? I think I said north first. We say that again. 70 miles per hour north is different than just 70 miles per hour, right? That picture of Indiana I drew on here earlier. We go 70 miles per hour, starting at Sellersburg, there's a fairly large area we could cover. Roughly 250 square miles. Just the formula for, oh wait, no more than that. 3 times 1,500 square miles. Roughly that. So a really, really large area, just saying we go 70 miles per hour. If we say 70 miles per hour straight north, there's pretty much only one spot we can end up with. So velocity is going to be a vector. We'll talk about this more when we get to the physics check. Velocity is actually a thing we want to change, kind of like driving your car. You don't control the velocity, right? You don't get in there and punch the keypad, go 55 miles per hour. We adjust the velocity up and down. And that's how we want to do a similar thing with our game. The inputs are already built in there. Gave us some gravity. So the default, it's already going to pull our character down. If I just hit run, character should fall down. So that downwards handle, we will see how to do some of the other ones. UI accept, there's a couple ones for that. We'll see input manager soon when we get a little more into Godot. UI accept, the enter button works for that. Then UI left and right, so that's going to be the arrows. And notice that it's an axis. Dimensions on a vector. Saw the word axis earlier. So those are the dimensions of that horizontal vector and a horizontal dimension. And in particular, those go from -1 to +1. -1 goes left, +1 goes right. And when we first press the key, it starts at 0. Like not pressing anything is obviously 0. So if we push the left arrow, it very quickly changes from 0 to -1 while we're holding the key, depending on how long we held the key. But very, very quickly, that one's pretty much going to count the way this is set up. That's pretty much going to be almost full, but if you try it a whole bunch of times to just tap it as quick as you can, you'd probably get some where you didn't reach all the way to -1. But it's a couple of milliseconds, so you're probably not going to tap it quick enough this time. Same thing, and then right goes towards +1. So then we have this value, this direction, which is somewhere between -1 and +1. And if we're not pushing any keys, it should very quickly go to 0. So we take that and multiply by speed, and that gives us a new x direction. So negative speed is so many pixels left in the x, positive x be to the right. That's the idea of how the movement works and working vectors in here. So if I comment out the gravity, we already saw gravity work and we didn't put, there's no shape, so we don't have a boundary or anything yet. We'll see that after we talk about physics. So I'm just gonna comment out gravity because we already saw that part works. Oh, and all I did there, highlight it, and then if you're using this editor, Control/, we'll comment that out, but that's common in most IDEs or most text editors. Control/ will comment out a big block of code. And if it's not Control/, it's usually Control K. Or Control-Shift-K maybe, but if we run that, then these built-in things give us that left and the right movement. So you see we're already using vectors. Kind of built in there. Get the axis and then we change this. I'm doing a 3D one that's almost the same. I'm gonna create a new empty thing. Make it a 3D node. Add to this a character 3D. And then add to that a mesh instance, and we'll talk about what all a mesh instance is and all that before long. Actually, on Wednesday. But maybe a this cube cylinder. That'll work. One of the shapes. So similar thing, but we have a character. We give this a save. Names probably don't really matter here. But when I attach the script to the character one, that script again, notice it's the character body 3D movement. Similar thing, we got speed and jump velocity. Gravity is coming from our project settings, which should be set up to, if we kept all our scales at 1, this will be an important thing we'll talk about keeping that straight later. It should match gravity. So if we make our characters like a 6 foot tall human, gravity should, the default version of gravity should be pulling at the right speed for that, right acceleration. Gravity is kind of the same, right? If not is on the floor, the name on that function is really clear. So if we're not standing on something, then just increase y by the gravity amount. Exactly the same as we did on 2D. Or decrease it. So negative y is down here. Positive y must be upward. Jumping is just going the other direction. But down here, it's a little bit different because, but not much, right? We still did input.getVector. And this time we pulled in four values instead of 2. But they're going to follow suit. They're going to be somewhere between -1 and +1. Down's -1, up's +1, left and right, or just like they were in 2D. We get that. And then we do some work with the vector. So here's the syntax to create a new vector. Pick some vector 3 that does not change y, x, y, z values, 3-dimensional vector for 3-dimensional space of x, y, z values. The gravity and jump button are handling the y, so we don't need to change that. And actually, when we start actually making a game, I'm going to erase this and do this the way I like to do it, and explain why to do that or alternative ways. But then we have that x and z. So that's forward and backward, left and right, but it's just moving left and right. I very much prefer like y'all pitch and roll, or instead of move to the left, we turn to the left, and then we're only move forward. Much more realistic movement. But we could use that to create a new vector, and then this. So transform, very important data, are transforms, position, rotation, and scale. But it has a basis. So this is that thing I was saying earlier. Every frame of the game, whatever we defined as forward for our character, so in this one, we can't really see it, but it's negative, I think it's -z, it might be +z. That changes engine to engine and thing to thing. When we get to graphics on Wednesday, Blender has z axis going up and then negative Y is forward in Blender. But then we bring it over here, it also rotates clockwise. Bring it over here, and we still get clockwise rotation, which is nice. But positive Z becomes what was negative Y in Blender. So there's a little bit of keeping things straight. Oh yeah, Godot uses positive Z for forward. Unity uses negative Z for forward. And I can't remember what Unreal uses off the top of my head. I'd have to double check that. But if I turn this a little, right, if we do something and turn it this way, oops, about that. I need something we can see turning. Can't see it turn. Maybe if I turn it this way. There we go. If I turn it this way, let me change that mesh. I can't see that thing turning. Box, that'll work. Okay, we have corners. So notice if we turn, what was forward is redefined. Right now, both of them line up. Turn this way. And the character's gonna have a new forward once we turn. So that gets recalculated at every frame in the game, based off what we originally defined this blue arrow to be. That's what this line of code does. Whatever the forward is, multiply that by the input direction, and then that gives us the direction we want to go in. And then once again, we're just doing some simple math, but well, this one's gonna fall again. Okay, around. Actually, we can't see anything here, can we? We're in 3D, so we can't see anything. I'm gonna click this button and add some light and skybox. Not much for skybox here.
Yeah,
Oh yeah. Thank you. And in 3D, we have to be able to see it. Work. We have to define everything, but we can see gravity still works the same. That's the default. That's the default. The defaults here in Godot makes it for really easy to get started. If I comment out gravity, then we can see the left and the right, forward and the back. Oh, not really. The camera is moving with it is why. Let me change it so that the camera was a child of the character body, so the camera moved with it. Now the camera is a child of the world, so if I use the arrows, you can see our default. Basically, all we did was say create a new script. So it's really, really easy to get things up and running, both 2D and 3D, once we get to it. We will be using vectors, but notice how it's built into the code. Oh, and then normalize. There's more than one normal version. Normalize here is gives us the length of the vector. So we talked about the normal direction earlier. That's just not what's always straight perpendicular to whatever surface we're on. Normalize, also referred to as just the vector norm, is the magnitude. I very briefly wrote it on the board earlier. That's the, looks like the absolute value, only we have two vertical lines instead of one. That's the norm of the vector, which is, so it's the length, but it's hard to work with lengths because here Notice this is direction. We want to separate the angle we're going at from the distance we're going in that angle. So normalize turns us back to a unit vector, so it has a length of 1. So we find the length and then divide by whatever that length is. So then we just have an arrow that's only 1 unit long pointed in whatever direction. And then we define that separately in our code. We'll see this in action a few times. Normalized mean the thing to remember is anytime you have this normalized as a function here, that means give your vector a length of 1. I need to run some stuff. Do I have more room over here? Okay, yeah, this will work. I'm just going to add some arbitrary stuff in here. So A is a new vector 2. So some sort of data. Then we can give it a couple numbers. So 3, 4. These are some of the ones we have in class. B around the board. B is another vector 2 type of data. Oh, I forgot a keyword. Not in Python. So we have to have the keyword saying create a variable. It's going to be vector 2 data or the walrus operator, whichever one is easier for you. Well, walrus operator is usually a little bit easier. 1, 2. That'll work. So I'll just print those out first, which means all this stuff's in the way. So probably didn't need to do that every frame of the game, but you can see the 2 vectors there. How it prints out our vector components. Actually, I'm going to do all this up in the ready function so that it only happens once. There we go. So we'll create a couple of vectors and then print them out one time. And notice it's just the word print. If you need some echoes while debugging your game, you can print out values and see where stuff's crashing. Print out. Made it this far. Made it to line 17, made it to line 20, and keep moving those echoes around to track down problems. We do math with them. So variable C, which is going to be vector 2 data again. Be A plus B. I think that was the exact example in the that was the exact example in that documentation, wasn't it? Probably could have changed it up a little bit, but I know bigger A is, again, if we take a vector 2 and add another vector 2, we still have 2 dimensions. We have a 2-dimensional vector and multiply by 12, we still only have 2 dimensions, they're just longer. So that'll be the vector A times 7. Then print those out. Print C, print bigger A. We'll be using these in much more interesting ways soon. Get that out of the way. Just get quick. That's not out of the way. There we go. So you can see we get correct thing when we add them and multiply them, which is basically the parts that we need in order to what we use most often. So our position, right? We had that starting position, that's just a vector. So if I print out position. And then maybe set another variable. Variable next spot is going to be, I'll do the walrus operator. Position plus bigger A. And then print that out. Probably doing more interesting things than print it out, but that's how we would get our next position, right? We do whatever vector math we need to find that adjustment to the next position. And then we can just add that to our current position. Run it and get that part out of the way. We'll be over there on the game scene doing this soon. I just wanted to simplify it. So notice from our starting position, so there's the movement we want to make. We're going to do the 21, 28. The vector goes 21 pixels horizontally and 28 pixels vertically. So positive y is down in the 2 dimension. The positive y is up in the 3 dimension. So that's a big change. But it goes 21 units horizontally, so to the right, and 28 units down, and we're going to add that to the current position. And then that'll be our next position. So it's going to keep moving, but also, yeah, let me go ahead and do this so we can see how far it's going to move. And we do the echoes here maybe for debugging. What we would normally do would be like our step size. So I can come up and create a global variable. That way it still exists. Vector2 data. It's going to be a new vector2 with whatever those numbers we put in here were. Bigger A. I'm just copying from print. 21, 28. I'll just type them right in right here. And y'all have seen code before. Written code and hopefully seen code in time restricted classroom examples. So we probably have a bunch of big fancy calculations to get to this point, but once we get to that point, we have that as a global variable. So then instead of all this stuff, what we want to do each time is take a position is going to be whatever position was plus step size. And then move and slide is where we actually do those. Move and slide means move to that next position and apply all the laws of physics. So friction and anything else, slide is like the abbreviation for sliding is something that definitely applies to a lot of physics, right? We have to be attached to the ground, so gravity pulling us down and friction moving along. So that means go ahead and make that movement. So every frame of the game now, we'll just take our position vector and increment it by this other vector. See what that's going to do once it runs. Yeah, probably really, really quick. I should probably do a smaller one. Yeah, that one's quick. This is, so when I said 21, 28, I was kind of thinking about seconds. That's how I think about time. In 1 second's time, I wanted to move that far.
Is that milliseconds?
So the thing about frame rates is when we hard code frame rates, we risk a big bug. So when we say make it 140 frames per second, the game engine is going to do its best to average 140 frames per second. Some will be faster, some will be slower than others. But we don't know exactly how long each one's going to happen because the computer is going to determine that at runtime. That's what this parameter that gets passed into this function is. Delta. So a math thing, let me write it on the board. This is going to show up a lot more in physics, but the Greek letter delta That means change. So delta t, change in time or time interval. That's sort of what we're thinking here. Time interval is a nice way to say it, but really it's change in time. And the formula for that is going to be the final time minus the initial time. End minus the beginning. We always want to go that way so that our negative sign indicates which way it goes with them, which way it progresses. Delta x is change in position. So again, that's going to be our final x position minus our starting x position. So anytime you see that delta, it's just the end value minus the starting value. And it basically means change. So that's worked into pretty much all of our game engines as a parameter we always have access to. And essentially what it is this is the number of milliseconds that the last frame took. So it's actually a little bit off, right? The game engine is doing its best to find an average of the number we asked for. So if we ask for 140 frames per second, that's 140 frames per second. Oh, the other way. 1,000 milliseconds per second divided by 140 frames, that's 7.1 milliseconds per frame. But some are going to be faster, some are going to be slower. It's going to be somewhere between 5 and 9 milliseconds per frame. So for our last one, and when the computer starts this frame, it doesn't know how long it's going to be, right? So all it can do is use the last one. Maybe the last one was 8 milliseconds long, but then the current frame ends up only taking 5 milliseconds. 5 plus 8 averages to 6.5, so we're really close to the 7. So it's a reasonable expectation there. But the last frame took 8 milliseconds. We don't know how long this frame is going to take, so the best estimate we have is just to use the last frame, length of the last frame. So I think that step size, that's a number of milliseconds. So then we can multiply that. Let me put some parentheses to make that clear. Delta, so the delta time in this case is really what it stands for, times the step size. So we're gonna take that little bitty number because it's given as second, it's milliseconds, but it's given as seconds. So it's a very small number because humans think in seconds, but computers move in nanoseconds. So it gives it as a very, very small percentage. So that's our scaling factor to scale down that vector by a whole bunch so that over the course of a second, we will move the number of pixels we thought of. That's more like what I was thinking of when I said move 21, 28 pixels, right? Takes about a second just to go a little distance. And there's going to be a lot of slow explanations like that in this class because of that thing we looked at earlier, right? It would have took 20 seconds to show how to write that code. We want to go deeper because of, remember what we looked at earlier?
Figure out why.
Origin on GitHub. Because ultimately, you're probably going to make custom game engines. You're not just going to make games with a game engine. Some of y'all are just taking this as a link to fill out the spot. It's like, oh, this is something. Others of y'all, which are very eager to talk about it, especially. So I think I know which ones already because you've already reached out to me about it. That's all you want to do in life, right? Is make games. So you all are gonna be making game engines, so we need to dig into those details. Why are we doing these things? What is going on? So that we're taking a really good first step on that path. Because yeah, I could have showed you how to write that code in what, 5 seconds? But we want to know the why. Why are we doing this? That way we can expand it into any situation we encounter. It'll get faster. Starting off slow. Some of it is also just so people who haven't had me in class before can get used to the way I lecture. You might have noticed I'm easily distracted. Try to stay on topic, but that's the first major component we'll need, vectors. Everything we do is going to be a vector. We can break it down, but we have to do twice as much math, right? Well, the code is next to each other. Let's look at that. The thing I commented out, we had stuff about the y component of the vector. Then we had a bunch of stuff about the x component of the vector. So the bare minimum, we need 4 lines to do that, plus the selection structures. Whereas if we just set up the vector, we can just do the vector math all at once. So ultimately, we want to be doing it this way. They split it up in the template to simplify it for newcomers, but really we should be working with the vectors every time. Makes our code a lot shorter. Makes your code a lot shorter and easier to follow because you don't end up with this .x all over the place. And the .y, you just have the one vector overall, which it might be more complicated. There'll be calculations leading up to it, but you'll have a line like this where you can quickly look and see what that vector is. And then everywhere else, you just refer to that vector everywhere, and you don't have to have all the dots and separate the x's and y's on the different lines and all that. So we'll be seeing a lot more of that. It's the first component. Next one's graphics. So on Wednesday, we will be looking at some 2D stuff. We'll use scalable vector graphics. Again, vectors that you can tie in there. And 3D vector graphics, that's the modeling. So they look different in the text file we use. Internally to the computer, they're about the same. So we'll dig in and look at how they're stored for the computer and what it means and how we look at it, how we see them in code. Although most of the time we're going to drag our mouse through pencil or something around to draw them. But when we drag the mouse around, that just writes code in the background. So we'll see what it looks like in the code, and then how those translate over to tie into the stuff from today, and then focus very in depth on the transform data. Everything we talk about this semester is going to involve transform data. It keeps coming back to that over and over and over again. That's the biggest one for simulation and game development, right from the name of the course. Does anybody have any questions about vectors though? I'll give it a few seconds so people on Zoom call can unmute or have time to unmute. Well, I assume 5 seconds means there's no questions. Silence means there's no questions. If you have any, let me know. I'm going to write a quiz. I tried to point out right along the way everything that was going to be on that quiz. And when I hit publish on the quiz, you'll have 7 days till the due date. So, right, if I hit publish at 5:15 this afternoon, then you'll have to 5:15 next Monday. I'll either write it this evening, this afternoon, this evening, by tomorrow morning at the latest.
You were doing the graphics one Wednesday, right?
Okay. Yes. Oh, the graphics quiz is already ready, but we'll cover all that stuff. We'll cover components and how to do it, and then I'll make something like that next week. But I've been doing graphics a long time. Like I've been doing 3D modeling. Well, actually, since the 80s, graphics was one of my favorite things to mess with computers. I became interested in 3D modeling when the original Jurassic Park movie came out. and I was in my early teens, and there were computers around, and it was very, very, very slow. But that's when I started learning 3D modeling, and it is still one of my favorite things to do when just pass the time is sit down and draw, sit down and make some 3D models. I really, really enjoy graphics. So I have what from 92 to 2024. I'll skip the 2D graphics because that goes even further back. 32 years of experience with it, which is longer than most of y'all have been alive. Also on my engineering degree, probably a lot of that was formal training, and not half, maybe about a third of that, somewhere around a quarter to a third of that was formal training in modeling software. So I have more experience than, yeah, I've been gaining experience with it for longer than y'all have been alive and have formal training. So I will do my best to not make it look too easy. I've done that before. Feel free to stop me when we get to 3D modeling, because I have lots and lots and lots of experience at that. And then formal training on top of lots and lots of experience, like years of formal training, not one lesson like we'll have in this class. So then after the quiz for the 3D model, and I'll probably come back and show y'all how I would make what did I put in there? Canoe. So canoe this time. So I'll show you what I would do to make a canoe, which at the speed that I would make it at. So, but I will wait until after the quiz is done. And that's the quiz that I'm going to evaluate graphics on. I'm not going to evaluate harshly on those, right? Everybody's at different levels. Some of y'all may have never done much of that at all, but if you're in this class, most software development, we separate front end and back end. We get to choose whether we want front end or back end. We can't do that in game development. They're too intertwined. So if we're gonna look at one, we have to look at the other. I will not be evaluating hard. So it's gonna be more feedback than anything. I'll tell you that way. That quiz is really a completion grade with lots and lots and lots of feedback. Based off years of experience. Like this might take you to the next step. Based on what you turned in, this would be a good next step to take, but that's not gonna be points off, because this isn't an art class. Art is just included. And beyond that, I'm gonna be asking for your own artwork throughout, but there won't be any evaluation on the artwork. That does not play into the grade, as long as it's your artwork. As long as you're not trying to pass off somebody else's artwork as your own. But we will talk about graphics on Wednesday. If you have any questions, let me know. I will send out an announcement as soon as I get that quiz put up and let you know when the due date is for it. See y'all on Wednesday.